All right. Well, welcome back, folks. Hope you had a good weekend and you were able to relax a little bit where you were at. I'd like to continue on this morning with where we left off yesterday, and that is we talked about I'm sorry, Friday, and that is we talked about the relationship between motion, energy, and temperature. So let me just go ahead and recap where we left off with yesterday on Friday, and that is we were able to talk about how a gas exerts pressure. A gas exerts pressure because it has mass and then it moves. Okay? So it interacts with it collides, it exerts a force with everything around it. Because so that's the pressure that it exerts on the environment. Okay, and so when we talk about atmospheric pressure, the reason why we experience atmospheric pressure is because these gas particles they bump into us, they exert a force over a certain area, and so there's a pressure that we feel from them. And that's how we know that the gases are there for the most part, that they exert a certain pressure on us. As the pressure changes, we know then that the gases will change as well. Either the gases will change because you have more or less of it, the change in mass, or because they're moving slower or moving faster. And that's what you got to make sure you keep this in mind. And all this will lead into the calculations that we will do in chapter 14, which I'm hoping that we can start on Wednesday. But you got to be able to make that link between the pressure. And so let's make sure you keep this in mind that the pressure that a gas exerts, okay, so that the pressure is going to be related somehow to the temperature and to the volume and to the number of particles, which is moles. Okay, and so we will talk about all of this in chapter 14. But in order to understand how temperature, volume, and moles and number of particles are related to the pressure, we have to be able to think about what's happening at the microscopic level. So we already saw then how number of particles here, the number of particles. Remember that's equivalent to the mass, how the number of particles affect the pressure, and that is as you increase the number of particles, the pressure increases. As you decrease the number of particles, the pressure decreases. Okay, so we talked about the extreme case of a vacuum where you have no particles, the number of moles would be zero, the pressure would be zero. Again, if you keep that in mind and that discussion that we had last week, it will help you with what we'll talk about in chapter 14. So all of this right now, what we're going to talk about will help us understand how gases behave. It will also help us understand how liquids and solids behave, and I'm hoping that we can start liquids today. But this is critically important, even though all of these are conceptual um, uh, uh, we're dealing with the pressure conceptually. We will be able to see how the conceptual nature of pressure of a gas will lead to and help you better understand how we can calculate for the pressure of the gas, changing some other properties. Okay? All right, so with that said, then where we left off with on Friday was with the discussion between temperature. We'll get to volume. We'll get to volume in chapter 14, but how temperature affects pressure. And that's what we want to be able to talk about. Okay? And so how does temperature affect pressure? Well, think about what we said then was temperature was the measure of heat energy. Okay? So that means temperature is the measure of this type of energy. It's the relative amount of heat energy, which means then when we are at a temperature, say at 0 degrees Celsius, as opposed to the temperature of 100 degrees Celsius, we know then that there's more heat at 100 degrees Celsius than at zero. So temperature allows us to gauge, allows us to measure the relative amount of heat energy. And so temperature is directly to heat energy. Okay? And so with that said, then the heat energy here can be also linked to so heat energy. So this heat energy, the energy associated with motion. Okay, so kinetic energy, remember we talked about kinetic energy, this energy is associated with motion. And so therefore heat energy, okay, and energy of motion, okay, are related. Energy of motion, which is kinetic energy, energy of motion, they are absolutely related. And in physics, you learn about how, we'll talk about this a little bit more, hopefully. Well, we'll see how far we get with this semester, but we talked about it in physics and AP chemistry, how energy can be, any form of energy can be converted to any other form of energy. So these energy transformations can occur between any forms of energy. So they are equivalent. So you can take heat energy, convert it to the energy of motion, which is kinetic energy. You can take light energy and convert it to heat energy, and so forth. So different forms of energy can be interconverted. And so that's what we're looking at here. We're looking at the relationship between heat energy and energy of motion. And so with that said, then we see then here, as the temperature goes up, which means then as the heat energy goes up, the kinetic energy goes up as well. So there is a direct relationship between heat energy and kinetic energy. Why do we need to know that? Because remember, what we talked about then was we were talking about how the movement of movement of gas particles contribute to pressure. So it's speed, how fast they move. And if kinetic energy here is a measure of the motion, and we saw in this equation here that kinetic energy is related to V here, which is velocity, which is how fast something moves, we see then that the kinetic energy, and if that's related, so as kinetic energy goes up, the speed of the particle goes up. The speed of the particle goes up, and if the speed of the particle goes up, and we saw how we did this. I did this analysis for you last Friday. As the speed of the particle goes up, the acceleration increases, and if the acceleration changes, the force increases, and the force increases, the pressure goes up. Okay, and so with that said, then that's what we're going to do moving forward. Okay, so and so with that said, then there is a relationship. If this is true, then there's a relationship between the speed of the particle and the temperature. Okay, so with that said, then as the temperature goes up, the speed goes up, and as the speed goes up, the pressure goes up. Okay, so you'll know that the pressure goes up, and the way we can think about this is because the gas particles will start interacting with each other more. They will collide with each other more, and as that increases, then the pressure also increases. Okay? So as the temperature goes up, the speed of the particle the speed starts to increase more and more. The acceleration will start to increase more and more, and so therefore the pressure will also increase. Okay? And so let me go ahead and write that down here for you. And so make sure you keep this in mind that what we're looking at here then is as the temperature, as you see an increase in temperature, and the inverse will also be true. As you see an increase in temperature, we're going to see an increase in the kinetic energy. Okay? And as the kinetic energy increases, we're going to see an increase in the speed, the velocity, which we'll designate as velocity. As we see an increase in the velocity here, we're going to see an increase in the force between the gas particles. And if we see an increase in the force between the gas particles, we're going to see an increase in pressure as well. This here, folks, is the link that you need to make between what we can measure with temperature and what we can measure with the pressure. We can measure the temperature of a gas particle, of the gases, and we can also measure the pressure. So in between here, you need to make, so this is a macroscopic observation. This is a macroscopic observation. The temperature we can observe, okay? Pressure we can observe, the force, the velocity, and the kinetic energies of the gas particles we cannot observe. And what we're linking here is the macroscopic, so this is macroscopic here. This is also macroscopic, which is what we can measure. And we are linking all that with the microscopic here, okay? So we can explain these two macroscopic observations here. We can explain these two macroscopic observations through this microscopic explanation. Okay, so we can explain those macroscopic observations, with these microscopic explanations here. Okay, and so that's what you need to be able to do. And I'll post this slide for you folks, but that's what you need to be able to do as we move forward. Okay. Okay. So let's go ahead then. Let's continue on and let's take a look at summarize what we left off with here. Okay. So if we can relate kinetic energy to temperature, okay, and that's what we need to be able to do moving forward, and that's what we talked about, then we can understand how the temperature is related to pressure. Okay. So make sure you keep this in mind then. That's important to make that relationship. But not all gas particles move at the same temperature, move at the same kinetic energy at a given temperature. Typically, you'll have some that move a little bit slower, some that move a little bit faster, but the bulk of these gas particles, the average, will move at a certain energy here. Okay, so when we talk about kinetic energy, we talk about an average rather than the actual absolute kinetic energy. Okay, so you want to make sure that you keep that in mind as we move forward. Okay, so with that said then, I'm sorry here. Let's go ahead then and let's take a look at this graph here. Okay. And this graph here will give you a better idea of what we have. So let me go ahead and explain this graph to you here. What we have then is plotted along the y-axis here, the number of gas particles and its speed. And remember, speed is related to kinetic energy. So we're actually also, if you want to think about it, measuring kinetic energy here as well. So even though we are measuring speed here in meters per second, So this is in meters per second. Okay, so that's the unit here. Even though we're measuring this in meters per second, this is also a good indication of kinetic energy as well. So, okay. All right, so let's go ahead and take a look at what we have here. Okay. We have, this is just one gas measured at 4 different temperatures. Okay, so 4 different temperatures, with the light blue here representing the temperature at 100 Kelvin, the dark blue at 300 Kelvin, the pink here at 600 Kelvin, and the red here at 1000 Kelvin. So temperature increases here. Okay, so remember, this graph here is particles versus versus speed, or thus the kinetic energy. Okay. All right, so what I would like to do then is let's answer this question here. Answer a couple questions here. Okay, so again, even though this graph here is comparing molecular speed, or the speed to number of particles, we can relate it to kinetic energy. So first question I'd like to ask you, which I would like you to answer on your paper then, is which point on the curve represents the average kinetic energy? Okay, so let me go ahead and ask you to answer this first, and then we'll interpret this graph when we come back. Okay, so answer that question. Okay. What happens to the curve? What happens to the curve as we increase in the temperature? So as we increase in temperature from 100 Kelvin to 1000 Kelvin, what happens to this curve here? Answer that question. And then I want you to provide a quick explanation for these two questions. You can explain what's happening here. So on your paper, folks, on your paper that you will submit for today, answer these two questions. Make sure you give a reasonable explanation, and then let's talk about it. Okay, so go ahead and get that done, and then we'll come back, take about a couple minutes to do it, and we'll come back, and then we'll go over each one of these points here. Okay. All right. Go ahead and get that these two questions answered. Okay. Let's go ahead and let's interpret what we have here. Okay, so let's interpret this graph first of all. Okay, so I'm just going to take one of these plots here, one of these graphs here to go over with you. Okay, let's take the light blue plot here. Okay, so what the area underneath this, what we're looking at here is that the number of gas particles, at a certain temperature here. Okay, so you have a few gas particles at the low. So if you notice here, following this curve, then at the low end of the speeder, you have not that many. You have a few gas particles down here, and then same thing over here. You have a few gas particles on the high end. Okay, so this is gas particles. So we're looking at this graph here. So at the very beginning, you have a few gas particles that are slow. So this represents a slow speed here. So this is slow, which means then low kinetic energy. Okay, low kinetic energy. And this region here, okay, if we take a look at this region, we have a fast. These are gas particles moving fast. They have high kinetic energy. But if you notice, there's not that many particles. This is a very small area of the peak here, and this is also very small. And again, we're looking at the light blue peak here. Okay. All right, so as we go up this curve here, we have this point right here. This point right here represents then the most particles. Okay, the most particles here. Okay, and this is if you take a look at this, and most of the particles then are sitting roughly around right here. Okay, so this is the in between. This is moderate speed, not slow, not fast. Okay, so therefore this is moderate kinetic energy, or what we refer to as the average. It's not too fast, it's not the low end, it's not the high end. And so when we talk about the moderate kinetic energy here, this is your average. Okay, which means then most of the gas particles here then will have then this particular speed. So at which point of the curve represents the average kinetic speed? At the peak, the top of the curve. The top of the curve represents the average kinetic energy, because that's where most of the gas particles move. That's the speed that most of the gas particles move at. And so if you have a few that are moving slow, a few that are moving fast, most of them are moving at this particular speed here, or this and thus the kinetic energy. So therefore we refer to this as the average. So it's at the point here, at the very peak here, here, and here. Each one of those represents then the average kinetic energy. Okay? All right, so that's the answer to the first question. Okay, so what happens then as this curve starts to as we start to increase the temperature? What happens to the curve as we start to increase the temperature? Well, let's consider this. If you remember from, I think you probably learned this in algebra, interpreting these graphs here. Okay, the area underneath this curve represents then the number of particles. So for our purposes, area underneath this curve here represents the number of particles. So, and so what you're going to notice here is that as we move from 100 degrees Celsius up to 1,000, okay, the curves flatten. Okay, they flatten, they get smaller and smaller, which means then they both represent make sure you understand this. All these curves represent the same area. They represent the same. We can calculate for that using a little bit of calculus, algebra 2, even can, but the area under the curve stays the same. What happens as it flattens, it means then more and more of the gas particles. Okay, so if this is your average kinetic energy here for the blue curve, okay, more and more of the gas particles will have a higher speed here. Okay, so what we're saying here then is as we flatten out this curve, more and more of the gas particles will have that higher speed. Okay, so what's happening here then is that the curve flattens. Okay? The curve flattens, that means then more particles move at a higher speed. And if you notice, the average kinetic energy increases. So if you notice here, as we move, this is our average, remember, this is our average, from 100 Kelvin up to 1,000 Kelvin, we are shifting the average to a higher and higher speed. We're shifting the average to a higher and higher speed, which means that the particles are moving at a higher speed, higher kinetic energy. And so therefore, because it's flattening, then we have more particles. We have more particles moving at these higher speeds. So if you notice here, this is a very narrow area here. And when we take a look at this here, this is a very broad area right here underneath this curve, this part, which represents roughly the middle. We have a much broader area than here, which represents more gas particles moving at this higher speed than what we have here. Okay. So the curve flattens, and the flattening the curve, then how can we relate that to the movement of the gas particles? We have more gas particles moving at that higher speed. Okay. All right, very good. Okay, so let's go ahead then and let's continue to examine this really quickly. Okay, and so if you take a look at this here, and I think this helps us to see this a little bit better. Okay, and then with this second graph here, what we're doing is again number of particles along the y-axis, and then this time we have kinetic energy at two different temperatures. We have T1 and T2. Okay. In this graph here, what you'll notice then is that T2, and hopefully you recognize this, T2 is going to be at a higher temperature than T1. Okay, so what you notice here then, and again, this is your average kinetic energy. This represents your average, remember. Okay, and this is your average kinetic energy. If you notice then, as we move from lower temperature T1 to T2, we have the gas particles, the average gas particles, we have more gas particles moving at the higher energy. Okay, and so kinetic energy at 2 is going to be greater than the kinetic energy at 1, and so the average shifts towards the right here, towards higher kinetic energy, which means then we have more gas particles. The gas particles all shift, so we have more. The gas particles then are all moving. They all acquire more kinetic energy. So therefore, then the average also here, then we have showing then the average kinetic energy, average number of particles here will also move at a higher average kinetic energy. Okay. Now, if you notice here, you'll still have with the second curve here, even at the higher temperature, you still have some that move a little slower, some that move a little bit higher, but on average, then most of the gas particles are here. We have shifted that average also to the higher kinetic energy. Okay. So as the temperature increases, the average kinetic energy of the particles then will also increase as well. Okay. All right. Okay. So what you want to keep in mind then is that when we talk about the average kinetic energy, okay, the part and the relationship here between average kinetic energy and temperature. Okay, so let's go ahead and we've discussed this already, that there's a direct relationship between the average kinetic energy and the temperature. So you want to make sure you keep that in mind. So as you increase the temperature, the average kinetic energy will also increase. And so make sure you keep this in mind, that the average kinetic energy of all the particles will, the average kinetic energy of the particles will always be the same for all of the particles at a given temperature, regardless of the physical state. And this is going to be important here. Okay? Regardless of the physical state, if you have a set of particles moving at a certain temperature, they're all going to be moving at the same rate. They will all have the same velocity. They will all have the same kinetic energy. So we'll learn this. We'll learn about this a little bit more, hopefully, in chapter 16 when we get to there. Okay? And that is water and all substances have, and we talked about this, at different states, they will transition to different states at certain temperatures. Okay, so we said then that water exists as a liquid at any temperature above 0 degrees Celsius. It exists as a gas at any temperature above 100 degrees Celsius. Okay, and then between and it exists as a solid below 0 degrees Celsius. So below 0 degrees Celsius, we have a solid of a liquid. Between 0 and 100 degrees, we have liquid. I'm sorry, at 0 degrees Celsius, we have solid water, ice. At between 0 and 100 degrees Celsius, we're going to have liquid water. And then at any temperature above 100 degrees Celsius, we have gaseous water. However, we have what we call then a triple point. Okay? At this triple point here, and every substance has a triple point, and this is a unique point for all substances. And at that particular substance, at that particular temperature, the substance then will exist in all three states. So every substance that we know about has what we call this triple point. And at this triple point, the triple point represents the temperature and pressure. We'll learn about this later. The temperature at which all three states exist. Okay, so the triple point for water then is at roughly about 0 degrees Celsius. Okay, so the triple point for water is roughly about 0 degrees Celsius, a little bit above, about 100th of a degree Celsius. Okay, at this temperature, okay, if you drop the temperature of water down to this temperature here and don't move it, okay, don't go above or below it, all three states will exist, which means then liquid water is in equilibrium with gaseous water and also with solid water. However, at this triple point here, now, and I'm sorry, I'm running out of time. I'll finish up with this. At this point here, the gas particles, the gas, the liquid, and the solid, all of the, even though these are different states, folks, so we have water vapors, liquid water, and ice, okay? All three are present at this temperature here, okay? They are all moving at the same speed. They're all moving at the same speed. They all have the same kinetic energy. And this is something that most folks new to chemistry and physics have a very hard time wrapping their mind around, that yes, they are different states, but the particles are moving at the same speed because they all have the same kinetic energy. Because kinetic energy is not dependent on temperature. Okay? Kinetic energy is not dependent on the physical state. Kinetic energy is dependent on the temperature. Okay? And so make sure you keep that in mind. And that's very hard for you folks, for new folks, folks new to chemistry and physics have a very hard time trying to understand. But the movement of these gas particles is solely dependent on the temperature, not the physical state. Okay. So what I'll do is I'll pick up with this discussion tomorrow, and then we'll start the liquid state as well. Okay. All right, folks, very good. Hopefully you have a good day. And like I said, if you have any questions, if you want to talk about this more combined, see me after school today. If not, I will see you tomorrow. Okay. Have a good day, folks.